So, good morning, everyone. Who here doesn't know about Yosys? Oh, that's good. That's good. Who here has ever done anything with a formal verification tool? Okay, not counting equivalence checks. That's good. Okay. So, today I'm going to talk about formal verification flows in Yosys, or more specifically, I'm going to talk about Yosys-SMTBMC, which is one of the formal verification flows I have in Yosys. So most of you might know Yosys for the stuff on the left side of this slide, various synthesis things like the ICE40 flow we did, or maybe Xilinx 7 series synthesis, and then using Vivado for place and route, or also one of the ASIC flows we have. But especially when you're doing something like building a synthesis tool, you have the need for formal verification yourself. And at some point you realize, actually when I have written a synthesis tool, I have already written like 80% of a formal verification tool. So it's not that hard to just add the missing pieces. So for quite some time now, we had various formal verification flows in Yosys. For example, there are a couple of built-in commands in Yosys to do formal verification. There is a assert command that you can use for bounded model checking and stuff like that. There is a separate framework for formal equivalence checking that can use hints like similar net names to make the problem easier. So usually when you use formal equivalence checking, or in many cases you have like your design before synthesis and your design after synthesis, and you would like to see if everything went right. And in this case, there are additional hints like internal net names that you can use to simplify the problem. Another method for formal equivalence checking in Yosys is just combining Yosys and ABC, using Yosys for synthesis of a meter circuit and then proving that meter circuit in ABC. The flow I'm talking about, however, the one on the top right on this slide, is Yosys-SMTBMC, and it's a flow that can use any existing SMT solver as long as it supports the right logics. I'm going to talk more about this later. And one of the big advantages of this is that it's very easy to swap out the solvers. And maybe you could have guessed different solvers perform differently on different designs. So it's a big advantage not being locked into one specific solver for something like that. Okay. Availability of various EDA tools for everyone, essentially. There is, on the synthesis side, a good availability of tools. So if you're a student, for example, and you would like to learn how to do HDL design, you can just download Vivado Webpack or something like that and get started within hours. However, if you're the same student and you would like to get to know how to do formal verification, there is nothing. For this presentation, I actually wanted to compare the performance of my flow with a commercial flow. And I asked around people I know. I asked at the university department where I do some research. Nobody there has access to something that is similar, that can run bounded model check. I know that these tools exist somewhere in the industry. But if I would be a student at my university and I would be really, really interested in that kind of stuff, I would have no way of trying it out and learning about it. So people in the industry are complaining that they can't find any verification experts to hire, and I really wonder why this is. Okay, in case you never read anything about formal verification, the really big message, the really important message, you will find a slide like this in practically every presentation about formal verification. When you do simulation to verify something, you only check a limited number of traces. So in this picture, all these circles represent states of my design. And when I simulate it, I start with an initial state on the left here. and then my design progresses through this state graph to the right. And in this case, we have 3 different simulation traces, and none of them hits the state that violates my assertions, which is the red or orange state. It's red on my slides. Apparently, it's orange here. So one way of dealing with this, of course, is simulating more different traces, right? I mean, if I just use random input and try it again and again and again, sooner or later, I'm bound to hit this red circle. However, if you look at this graphic very carefully, you will see there is only one way to get from an initial state to the red circle. And one of those traces almost made it. But if you multiply all the choices you have at each node, you will realize you can run this 1,000 times, and you still have less than 50% of hitting this one state that violates my assertions. And obviously, this is just a comic, right? I mean, when I have a real design, something that's really worth checking, then usually my state space is not something that would fit on a presentation slide. Usually, my state space has more states than there are photons in the universe. So, so that's not really the way to go, to simulate over and over again, if I really would like to make sure that my assertions are never violated. However, formal verification uses symbolic methods, static execution, or whatever you would like to call it, to evaluate the entire graph, not just sample one specific trace. And therefore, when the formal verification tool says this state is unreachable, then it really is unreachable. And I can be sure that my design will never hit this this red or orange circle. Good, so that's what formal verification is about. We would like to make sure that our design meets specification. So when would we use it? And the usual answer to that question is, well, if you have a critical application, if you are building a satellite, if you are building medical equipment, then you really have to make sure that you meet specification. However, most of us don't do this stuff. Most of us do other things. Most of us don't build satellites. My impression, however, is that the companies who build formal verification tools, they only target this market. They say, if you build a satellite, you have no other choice. You have to use formal verification. So we can build them whatever we want for our formal verification flows, and it doesn't matter that all the other application areas that might benefit from having access to formal verifications don't have access, because in the end it's more profitable for us to just target this one specific area. And in my opinion, that really is a big problem also with the perception of formal verification. Because most people see something about formal verification, read something about formal verification, and they think this is somebody else's problem, and I can't benefit from this because I'm not the guy who is building a satellite. However, I would argue that there are 2 other areas where formal verification can be very, very useful, even when you don't do critical applications. And the first one is bug hunting. So the difference between bug hunting and proving the design is correct is that with bug hunting, you still leave gaps. But it doesn't matter. If you find 10 bugs, you found 10 bugs, and you have 10 bugs less in your design. Maybe you're not able to prove that there are no bugs left, but those 10 bugs, they will never worry you again. And one big difference between bug hunting and proving that the design is correct, if I would like to prove that the design is correct, then I need a full formal specification of the correct behavior. But if I would like to do bug hunting, a partial specification, only some part of it that I know it should behave this or that way, is already enough. It might be sufficient to show that there are some bugs in the design. And it's much, much easier to get to these partial specs. Also, it's okay to take a large proof and just fraction it into many small proofs. You can't really do that if you would like to prove that your entire design is correct, because then you are left with another proof. You have to prove that all your fractions overlap and are in fact complete. But if you're just interested in bug hunting, it's okay to assume stuff like that. And then you have something that might be much, much easier to do. Another thing is optimization. When you have a core, and now it does what it should do, sometimes you don't feel you're finished. Sometimes you think, okay, and now I'm going to optimize it. Usually when you optimize a core, in many cases when you optimize a core, you add special handlings for special cases. Let's say you would like to power optimize something, and now you add clock gating. And you know your design works without clock gating, but now you have to make sure that you don't accidentally clock gate something and an important value doesn't get propagated because of that, because you made a mistake. In this case, you can use the design you already have as a specification and proof against that. So in some cases, this is just equivalence checking, but in other cases, you might have a different timing, for example, but you would like still to be able to compare the output of both of those versions of those cores. And you don't need a formal spec for that. You just need the known good reference. So I'm not really going over this slide. I just would like to mention that it's really easy to install this. You just go through this procedure. It's not like you have to manually build 20 different dependencies that have been written somewhere in the 80s and an ancient Fortran version or something like that. If you would like to try this out, I would recommend you download the slide set. The link for that is at the end of the presentation. You can also download a lot of examples that are available on the same website. You just follow these instructions if you have Ubuntu or Debian-esque operating system, and you're good to go. I think if you're willing to invest another hour after listening to my talk, you should be able to really do some of the examples here, play around with them, and yeah, maybe this could be fun or even useful. Okay, these are the examples. So let's get right started with a little hello world example. I'm going back to some more theory-like slides after that, but then at the end, there are more and more examples. In this little hello world example, I have a counter, and I have a reset input. And if the reset input is high, I reset the counter to 0, and otherwise I increment the counter. So it's not a really complicated design. And I assume that the counter never hits 10. So this is the, let me see, this line here. I assume my counter is never 10, and then I assert when that counter never can become 15. And you as a human might look at it and might say, okay, that's reasonable. If you can't even count to 10, it might never go to 15. But I mean, we have to start somewhere. And here in the lower right, we see the commands that are needed to prove this. First, we use Yosys to synthesize this design into an SMT2 file. This is not a complete SM2 input file, it's just a fragment that represents the design in the SMT2 language. And then I'm using a separate program, Yosys-SMTBMC, and I give it this SMT file as input, and it's now going to prove that the assertions in this design hold. The first call, the red one here, will just run a bounded model check for 20 cycles. And the second call, we use temporal induction, or K induction it's sometimes called, to prove that these properties actually hold forever and not just for the first 20 cycles. And if I run this, I get this output. And indeed, it passes the bounded model check, it passes the induction step, so we know that the properties in this design are true. And if you would download all this stuff and play around it, the first thing you try out is comment out the assumption and then see if it actually fails. Yes? Oh, no, there is rec count equals 0.
Ah, okay. I got it. I was looking for the initial statement, didn't think there was an initial statement, and then I figured it should have failed in the next step if it didn't have an initialization.
That's a very good point. That's another thing you should try out. not only comment out the assumption, also comment out the initialization, and then it would also fail, yes.
Thank you.
So if,
Okay, in this example, you got rec count is 0 as an initial state. Pretty much all ASIC tools bar from these statements. You cannot have a flip-flop that comes up in a known state.
yes. You can, in your synthesis script, get rid of all initializations if you want, then everything is uninitialized. You can also make an initial assumption, for example, or a formal test bench, I'll show this later, to make sure that during your verification that the sign is reset properly, so that everything that is reset using the reset signal is actually reset during verification, but everything which is not initialized by the reset signal is uninitialized, which in this case means it can have any initial value. So this flow is not doing proper X propagation, but there are other flows within Yosys for formal verification that can also do X propagation. So then it's really initialized to an X, and all the Verilog rules for propagating X's are applied.
Okay, so this will work without initial...
Yeah.
Okay.
But this example, of course, would fail because it depends on the initialization. I had to fit it on a slide. Good. So if you are used to writing normal Verilog code, then you probably haven't seen this assert and assume statement before. There is even a third one, restrict. So I'm going to mention quickly what they do. The assert statement just outputs an error, produces an error if the expression evaluates to false. So that's more or less what you would expect. Likewise, the assume statement assumes that something happens, that it assumes that something is true. So for simulation, it's actually the same behavior as assert, because in simulation, everything is determined. So in simulation, it will say an error, your assumption is wrong. However, in formal verification, it will only consider traces for which this thing holds. So we have seen this, we've seen the counter will never reach 10. This was an assumption, so all traces where the counter would pass over the value 10 have been ignored. The third statement is restrict, and now restrict is ignored in simulation, but for verification it has the same behavior as assume. So this naturally brings us to the question, when would you like to use assume and when would you like to use restrict? And the rule of thumb is you use assume when your asserts would fail without the assumption. However, if you just would like to not consider some traces to help the proof, to make the proof progress faster, but at least you think your assertions would also hold without this assumption, then you use the restrict statement to do that. And of course, there are exceptions where for one reason or another, you prefer to use a different statements. For example, in Yosys with the Verilog frontend, there is a flag to say ignore all restrict statements or ignore all assume statements. And sometimes you use restrict or assume because you would like it to be ignored using this flag. So there are two different kinds of assertions or assumptions in Verilog. There are immediate assertions and concurrent assertions. Immediate assertions essentially mean in a behavioral block like initial or always, and then you just use it as a statement. However, concurrent assumptions are used in module context, and you say assert property, and it should just hold forever. And usually, with system Verilog, you could use a system Verilog property here. However, Yosys doesn't really support system Verilog properties at the moment. So at the moment, this is just an expression that's allowed here. So right now, a concurrent assertion is essentially equivalent to an always at star assertion. There are plans to support more of system Verilog assertions and properties in Yosys in the future. Right now, I would say in most cases, you just would like to stick to the immediate assertions that are using always blocks or initial blocks.
System Verilog adds the always comp construction for one particular reason, because always comp is evaluated at T0 and always at star is not evaluated at T0. You just said you're running on initialized values, so this assert will not be executed at T0.
You got me. It's going to be, because this is not a simulation. And for Yosys, always at star and always comp is exactly the same thing.
Okay.
Okay. So, formal test benches, or at least I like to call them formal test benches. So when you do a simulation, you have your design on the test, and usually you write a test bench that like creates a stimulus for your unit under test, so you can test it. And in some cases, you don't need something like that for formal verification. You just have a module, and you have some assertions in there and some assumptions, and you say, is this true? However, in some cases, you would like to have a wrapper around it that makes sure that certain things are true. And this could, for example, look like this here. We have on the upper left, essentially, our module from before, this time without initialization. And on the right side, we have our formal test bench. And here, we have an initial begin, and in the initial state, we assume that reset is high. And for all other states, reset can be whatever the top level reset input is. And in everything that is not the init state, $init state is a Yosys extension, we have the same assumptions as before. So now we have a module that does not have any assertions or assumptions in it, but we have a wrapper for the formal test bench, and this makes sure that the stimulus looks in a different way, and yeah, and we assert the same thing. We say the counter must never reach 15. Good. So, supported SMT solvers. That's the main point of Yosys-SMTBMC, that you can use many different SMT solvers. In principle, you can use really every SMT solver for the simple reason that all the logics that I use are optional. So I can use synthesis within Yosys to synthesize everything to a gate-level netlist, and then I don't need bit vectors. I can synthesize arrays to flip-flops and muxes, and then I don't need a theory of arrays. I can unroll everything I do with uninterpreted functions. So in fact, you can just use SMT2 core. However, most solvers support a little more than that. So usually you would like to make sure you use the features that your solver actually provides. It's tested right now with set3, CVC4, Yikes2, MathSert, and Boolector. I've always done tests with ABC, but there are still performance regressions with ABC. And usually I recommend set3 and Yikes2. The reason is these are the two solvers that support all the theories that Yosys-SMTBMC can use. So you don't need to think about, is this array so large that I can't use a solver without support for arrays, stuff like that. Set3 is under a permissive license. Yikes2 is under a non-commercial license. However, all of those solvers are available in source code form, which is kind of an interesting thing. And usually Set3 for reasonable problems yields good results. So here I've tried make check with Pico RV32, which checks some properties in my Pico RV32 CPU. We see the overall dynamic range is 10 orders of magnitudes if you include my estimate for how long it would take for CVC4 to complete this example. I'm honestly not using CVC4 for a lot of things. Otherwise, we still have something like 1.5 orders of magnitude span between the different solvers here. However, this is not like Yikes is always the fastest one and MathSert is always the slowest one. It really depends on the specific problem you would like to solve. And in some cases, it really pays off to experiment a little bit and try different solvers. So, just another few terms I'd like to introduce, bounded and unbounded methods. Bounded methods basically mean we only check the first n cycles after the initial state. So this can be very useful for many cases, but it's certainly not what we always want. In some cases, we would like to prove that our properties hold forever and not only in the first 10 or 100 cycles. And this would then be an unbounded method. So BMC, like Yosys-SMTBMC, BMC stands for bounded model check, so that's a bounded method. We check that something holds, that the property holds for the first n cycles after the initial state. However, there is temporal induction or K induction, and it's a method to extend this and basically build upon a bounded model check and try to prove that the property will hold forever. In the next couple of slides, I'd like to explain to you how this is done. So in a bounded model check, the easy way to do that is to create a couple of symbolic states. So in this case, the circles represent symbolic states that can be any state in the design, and say there must be state transitions. So now there are 4 consecutive states. And then I add additional checks that say all these states must comply with my assertions. And if they don't, give me an error and produce a counterexample. So this would be the naive way of doing a bounded model check. Usually it's done a little bit differently. That's what we see on the bottom half of the slide. Usually we start with one state and just say, is there one initial state that violates my assertions? And if there is such an initial state, then we are done. I don't need to check any other states because my initial state can already violate my assertions. However, if this fails or succeeds, however you would like to look at it, so if we find out that the initial state always complies to our assertions, we construct a different proof. And this time we say the initial state, we assume all assertions because we have proven already that we can do that, and we only check the state we add, the new one. And this way we incrementally build a larger and larger proof, and in most cases in practice this is much, much faster than the naive approach. So for temporal induction, we build on this. So we start with the same 4 states we have before and we make a proof. Doesn't matter which of the 2 techniques we are using. We make a proof that the initial state and the 3 states that follow, they don't violate any assertions. And then we create another proof. And in the second proof, we don't have an initial state. We just say, assume there are 3 consecutive states that conform to our assertions. And then we try to find, is it possible to have a 4th state that follows that does violate my assertions? And because we have already 3 states here to start with that conform to the assertions, we have already significantly reduced the state space we are looking at. And if we are lucky, this proof succeeds. And now we can say, okay, whenever we had 3 consecutive states that confirm to our assertions, the next one will also assert. And now I have 3 new ones, and the next one will also assert. So essentially, yeah, the name says it. When you have ever done induction in math, then it's exactly the same idea. Good. So let's look at this at a more realistic example with such a state diagram. So the inner bubble are the reachable states. So of course all initial states are in this inner bubble, and if we follow the arrows that represent state transitions, you can see we can't escape this inner bubble. However, the formal verification tool never sees this picture like that, because as I said, usually you have more states than you have photons in the universe. So so all the formal solver can do is look if there are specific patterns in this entire diagram, like 3 states that match the assertions followed by a 4th state that violates the assertion. And in fact, we have something here. So, so if we look here, we have 1, 2, 3 states that conform to our assertion, but this one is followed by another state that violates the assertions. So in this case, the temporal induction proof would fail, even though we can see none of the states that violates assertions are actually reachable. So when the temporal induction step fails, it doesn't necessarily mean that I have an error in the design. It just means I haven't succeeded in proving that there is no error in the design. And then I have a couple of things I can do. For example, I can increase the induction length. So in this case, if we say 4 valid states followed by an invalid state, that is still possible. 5 valid states followed by an invalid state is not possible anymore. I can't fit 5 invalid states in here. However, here I have a circle. And here I can fit 100 or 1,000 valid states followed by an invalid state because I can stay in this circle forever if I like. So in the left example, I have to do something easy. I just increase the length of my induction. In the right example, I have to look at the counter example the solver gives me and add a new assertion that tells the solver that at least one of those 4 states that built the circle is invalid. Then I've broken the loop and I have successfully proven what I'd like to prove here. So this is the usual workflow. I'm a little bit behind time, so I'm skipping over some slides here. One important thing with the whole idea with using SMT solvers instead of SAT solvers is that SMT solvers allow me to have a higher level representation of the design. I can use arithmetic operations. I can have arrays as really objects in SMT. And this is good because it allows me to preserve problem structure. And usually, if I preserve problem structure so that the solver has a better chance of understanding the structure of the problem, then usually the solver is more efficient. And there are 4 things I do with Yosys-SMTBMC to preserve problem structure. The first one is I don't synthesize everything down to gate level netlist. Instead, I use bit vector logics in SMT-lib to make a word-wide RTL type representation of the design. I don't necessarily synthesize memories to muxes and flip-flops. Instead, I'm using the theory of arrays. I don't flatten the design hierarchy. Instead, I'm using uninterpreted functions to model hierarchical elements. And this means if I have a module, a hierarchical module, and I instantiate it 1,000 times, the module still has a chance of recognizing that this is 1,000 times the same thing. If I would unroll this, if I would flatten this design, finding out that this is just 1,000 instances of the same thing is actually in itself an NP-hard problem. So it's probably not a favor to do this for the solver. In fact, instead we should let the solver make this decision on their own and maybe annotate it somehow so that he can still use this information that there's some structure here. And the same thing for time steps. If I have a really, really long temporal induction proof, then I essentially have the same circuit instantiated like 100 times. And I'm, again, using uninterpreted functions to preserve this structure. So this is the overall flow. You take your Verilog design, you take your asserts that are part of the design, maybe additional checker modules or test benches. You run it through Yosys. This gives you SMT2 code. Then you run it to Yosys-SMTBMC. You add an extra constraints file. Yosys-SMTBMC is using an SMT solver, and it can use any one of a list of solvers, and it produces a pass-fail output. And in case of a fail, it produces a counter example. Right now, there are 3 different file formats I support as output for the counter example. It can produce a VCD file, and you can just look at it in GTK wave or whatever. It can produce a Verilog test bench, so you can run it in a simulator and make sure that this actually is the problem that the solver claims to be. This can also be very interesting for proofs that run for a while. So you have something that runs for an hour, and then it produces a counter example, and then you make a small fix, and you would like to make sure the fix actually worked. The first thing you can try is use this test bench to see if it now fixes the problem if you run exactly the same trace. And it can produce a Yosys-SMTBMC constraints file. So if I take this constraints file on the right and put it on the left in this picture, I would instantly produce exactly the same counter example again. However, I could take this constraints file and, for example, if I have a very long proof, which is 100 cycles, I could just remove the constraints for the last 10 cycles and then use this as something which runs faster, but probably will check the same thing if I make changes to the designs and I would like to check them first with a faster run before I rerun the entire proof again. So the typical workflow here is a two-step workflow. You've seen it in the example before. We start with a bounded model check. This is just Yosys-SMTBMC without the -i option. And if it fails, we know there is a problem. And you have to either fix your design, or you add additional assumptions, or you have to loosen your asserts. But you have to do one of those things. There is a problem either in your design or in your specification. If it passes, good so far, and we proceed to step 2, which is the temporal induction. That's now SMTBMC-I. So if that fails, we have to investigate the counterexample, and we have to decide, is this reachable or is this unreachable? And if it's reachable, we have exactly the same thing as before. If it's reachable, there's a problem, either in the design or in the specification. If it's unreachable, we have to find a way to explain to the solver why it is unreachable. And we do this by adding additional assertions. For example, by breaking the loop, which I've shown before. If it passes, we could either say, okay, we are done and we're happy, or we can say, I'd like to have more assertions in my design. Sometimes this is a problem. People start with like 1 assertions and they feel like I should have more assertions in my design, but I don't even know where to start. It's quite easy. You run a temporal induction. You prove that your assertion holds, but maybe you have to run a temporal induction proof that is 10 steps deep. Then run one that is 9 steps deep. Look at the counterexample and see what assertions you have to add to explain to the solver that this 9 steps deep counterexample is also unreachable. Sometimes when you add additional assertions, things get worse. So this is the example from before. And where's my mouse cursor here? And if you look here on the left, there is no problem here. We have some states that are unreachable, but stay within our bubble of assertions. And then they go into the bubble of reachable states. However, let's say we are going to fix the one on the upper right, and we are adding an additional assertion that now makes this state here invalid, so we break the loop. But maybe this will also make this state here invalid. And then we will get a counterexample that terminates in this state. So sometimes you add additional assertions and the problem gets worse, but actually you have made progress, because ultimately the goal is to reduce these outer assertion bubbles in size so it fits exactly the inner bubble of reachable states. So in practice, we never can really do this in most cases, but this is usually the goal. And the better we are at this, the faster our proof will run. So usually when you do formal verification, you add more assets, and maybe in the short term, if I add an assert and this bubble in the lower left, this one circle becomes invalid, maybe my proof gets harder because now I have to increase the induction length or something like that. But in the long run, if I have a design with 1,000 asserts and a design with 2 asserts, probably the design with 1,000 asserts would verify much, much faster, because there is much less crap in this gap between the reachable state and the bubble from my assertions. So, I have a couple of additional examples, and I think I'm now exactly 40 minutes, is this right? I'd like to maybe mention a few of them to get a better, to give you a better impression what this all looks like. So this is a variation of the first hello example. Now we have a mode thing, and the mode thing says if we count up or if we count down. And initially we assume that the counter is 5, and we say the counter can never be 200. And in fact, if we look at the always block above, we can see it can never go below 0 or above 99. However, if we try to, so this assertion holds. We can never go above 99. However, if we try to run a temporal induction for that, we get a counterexample, and the counterexample just starts somewhere at 194. So this assumption is actually never, so because we start already beyond 100, this is a valid counterexample. Somehow it would violate this initial assumption, but because we are doing the initial induction step, we don't care about the initial assumption anymore. So we have to find a way to tell the solver that this counterexample is not reachable by adding additional assertions. And in this case, it's quite easy. We just say, okay, the counter never can be greater than 99. Maybe this would be a wrong assertion. Maybe I've made a mistake in my head. But then I will get another error when I run formal verification. This is not an assumption, this is an assertion. However, if this assertion holds, and this is the case here, then I can successfully prove that this circuit will never violate its assertions. Yeah, I'll do that again, and I'll just mention the others. Is this okay? This is just one of many things you can do with Yosys-SMTBMC that is maybe an unexpected feature. Let's call it let's call it that. I'm not sure if commercial tools can do something like that. I'm sure there are some. Some of you might know there is this parallel case attribute in Verilog where you can tell the synthesis tool that the cases in a case statement can never trigger simultaneously. They are strictly exclusive. Usually a simulator will just ignore that. So if you make a mistake here, your simulation will always say everything is fine. Your synthesis might break. However, it depends on the kind of synthesis tool. You can use a FPGA synthesis tool and test this for hours and days, and there will never be a problem, because maybe the FPGA synthesis tool just didn't find a good way to use this parallel case. And then you go for your ASIC, and you run your ASIC synthesis, and it's a different tool, and maybe this tool is a little bit smarter and knows how to utilize this parallel case, and suddenly your design breaks. So this is something that you really would like to catch early, and you can do this with Yosys-SMTBMC. In the synthesis script, we just add one additional statement, assert pmux, and this essentially adds additional asserts to your design, making sure that this parallel case thing holds. And it uses the context of the case statement. So we see here is an if statement, and if you're not even reaching this case statement, then we don't care if this parallel case is really parallel. But if we are using it, then this must hold. And in fact, in this case, it doesn't hold, as you can easily convince yourself. But you can also just trust the tool, and it says there is an error in parcase.v line 6, and that's the case statement here. So if you download the examples I've given here, then there are a couple of other things that you can try out. So here is a non-trivial check that compares two different implementations of memories, and that's using some things you can't easily do otherwise with other tools, because I say in the initial state, these two memories in these two hierarchical instances are the same. They have the same content. I have some examples with PicoAV32 for checking more complicated stuff, like the AXI master interface of PicoAV32. There are a couple of properties you would like to check with an AXI, a couple of easy ones, but also a hard one. The hard one is that a rising edge on axis valid must never depend on a rising edge on axis ready. And that's not so easy to formally verify. But this is the relevant code. It does this verification for PicoAV32. Essentially, I make two instances. They are the same. They start up in the same state. and then one of them sees a rising edge on ready, the other one doesn't, and they must not diverge in their behavior. You can also check liveness properties if you want, and there are some tricks to make this work for real-world examples. And I've also done some benchmarks that I'm not really showing you now. And I also would like to mention that you don't need to use Yosys-SMTBMC. You can also write your own proofs and just use the SMT output from Yosys to construct your own proofs. I also have an example here. This design here, when you plot the state graph in your head, you will see there's a circle. You can go from state 2 to 3, from 3 to 4, from 4 to 1. And we would like to show that there is such a circle in this design where actually I return to exactly the same state. And I could do this actually with Yosys-SMTBMC with a custom constraints file, but in this case, I just wrote my own SMT code to do exactly the same thing. If you would like to know more about the way your design is generated using the SMT backend in Yosys, then this is probably a good starting point to investigate this and play with it. Yep.
Thank you very much, Clifford. Great thing. Maybe you can talk about the future work. You skipped over it. You skipped over the future work slide. I think it may be interesting to
I'm already at 50 minutes, so...
Yeah, it's okay.
I'd love to talk about future work. So the next thing I'm going to do is system Verilog properties, better support for that. However, I would like to advise everyone to not use too much system Verilog features because it doesn't look like there will be really good support over the whole open source toolchain for system Verilog stuff anytime soon. So I think using immediate assertions is probably the way to go. I would like to support X propagation in this flow as well. Right now it's only supported in another flow. And I would like to make a C backend for Yosys, which would make it much easier to either verify HDL designs against C specifications, thinking of stuff like Spike here, for example, or writing a Verilog specification and then using that to check that against the C specification before using the Verilog specification to check your actual design. This is the link where you'll find this presentation slides, the examples I've been using, and all the other stuff.
Okay, so one question. Essentially what you're doing is you formally verify the Verilog code that people have written. You have your essentially modified synthesis, or like the synthesis that is not used exactly as if you do an ASIC or an FPGA. So based on your experience and that every tool has the more bugs, the more you get closer to a netlist, is that a valid assumption to make this as an assumption that commercial tools make as well?
So first of all, I can't say much about commercial tools because this is actually the only tool I've ever used to run non-trivial bounded model checks. Usually you have a couple of different checks you run. You run checks that you use to verify that your properties hold, that your Verilog code conforms to specification. And then you run checks that make sure that your Verilog code actually is equivalent to the synthesized netlist. And for these equivalence checks, you can do equivalence checks with this as well, but it's better to do equivalence checks with the other Yosys flow, especially there is this equif underscore set of commands that can be used for that.
Thanks.
Andre Powell, I haven't had that much exercise today. The two questions, in actual fact. First one is the fact that you said that you can do system Verilog. Can you do very deep multi-dimensional array checking?
No.
Okay, cool, that's that. Second thing, and I suspect you're going to say no to again, is there any chance that at some point in the future you might do a VHDL equivalent?
So I'm not going to do VHDL myself. However, there is a project called Yodel, Y-O-D-L. And that's a VHDL front end for Yosys. It's under construction, but they can already pass nice-looking VHDL code. So I'm not really sure how it will perform on real production code that's out there. I don't think they are thinking about assertions and assumptions right now, but this is the easiest part to add, probably.
Further questions?
This is Stafford. It's a very basic question, and maybe I missed it, but I saw in your demos that you would run a command, but I didn't see where you specify like a clock is a clock, or these other ones are inputs.
Yeah, right now, so there are a bunch of small to-do items I have on my list. I didn't mention them in future work. And one of them is to actually support multi-clock systems, essentially by emulating it, by sampling signals and having like a hidden global clock, and when it sees a transition on one of the real clock lines. So it's actually independent to add multi-clock domains from the actual flow, because it's a transformation of the design. And right now, all the clock lines are ignored, and we just assume that all flip-flops toggle synchronously.
Cool, then. Let's think. Oh, we have another question.
I'm just wondering, do you support the popular synthesis constructs of system Verilog, like interfaces and so on in Yosys?
Right now, no. So this is one of the things that are on the to-do list for supporting more system Verilog features. But I'm not sure when I will get to it. The overall theme will be stuff that I can easily implement using an AST transformation. Will probably happen sooner or later. Stuff that would require more work than just an AST transformation, I'm probably not going to invest any time with that. So interfaces probably gonna be there, but I don't know. Multi-dimensional arrays or arrays at all that are passed to as parameters to models, this is something that I will never support. Let me just quickly go back to the multi-dimensional array question, because I now mentioned it again. The Yosys frontend supports multi-dimensional arrays. They are just going to be flattened, and therefore if you have an over or underrun in one array dimension, it will just address another element and not say, oh, this is an error.
So let's thank the speaker again. Great job.